All right, so for the last kind of topic we're going to talk about, this will be part of your final homework assignment, which is only going to be a couple problems similar to the example here. We're going to talk about impact forces. So some object is in following, say, harmonic motion, and then at some future time, capital T, some other object collides with it and gives it a force either up or down at a certain instant in time. And again, if you read through the notes that I have in this week's folder, where it explains that we can't really use an impact that takes zero time. It doesn't happen at an instant. It actually happens over a small interval. But the notes illustrate that if we view it as an instantaneous impact, it doesn't affect our final answer with very much error. So it's a good approximation, and it makes the work a lot easier, as we'll see, because we don't have to compute convolutions. We can really just observe what their values are without really computing anything. So to do this, we want to model a magnitude of a unit magnitude 1. We use this notation delta of t minus t. It's just, we're thinking of this Dirac distribution delta as a function, even though it's not really a function. It's a process defined by a limit. And this t minus capital T is just a shift in time. So we're saying that this impulse occurs at time capital T. So some basic properties. Here's the definition of what this Dirac distribution is. If you're given a function g, then integrating g multiplied by this Dirac distribution with a shift in it to time capital T, this integral is really just this following limit that we have here, because remember that it's defined as a limit of a difference between two of these step functions that we called u, which are 0 for t less than 0 and 1 for t bigger than 0. So by playing around with the notation, it really just results in this limit. But if you look at what this limit actually is, it's just computing the average value of g of t over the interval from t minus c to t plus c, where c is some small number. So each of these values for any given small number c is just an average over an interval that's centered at the time capital T. So if we shrink that interval down, those averages converge to the actual value of g at capital T. So this is the nice observation about how this limiting process works by shrinking our interval of impact time down to an instant. It makes computing this convolution, or computing convolutions, much easier. We can basically just plug in values and we know what we're going to get. So for example, if I had to compute an integral of the following type, I don't have to actually compute those limits and then to compute those averages and compute a limit. It's going to be the same every time. It's just take our function, which in this case is t squared minus t, and we just plug in 6, and that's what we get. Generally speaking, you have an integral with the delta function multiplied by some other function. You just take a look at the input of the delta function and you solve that for the integration variable. Set this quantity that's highlighted equal to 0, solve for t, and then that's your value you're going to plug in for t in your other function over here. That's really all that it's what you're doing. So again, even though this is not a function, computing its Laplace transform makes sense because we're just integrating this delta function times an exponential. So again, by what we had on the last slide, this quantity highlighted is 0 if lowercase t is equal to capital T. So for lowercase t in our other function, I just plug in capital T, and that's where we get that. So we're thinking of this as our force function, our impulsive force function, even though it's not a function, but its Laplace transform is a function given by this exponential. So recall we did in the last video we were talking about an impulsive force where the force turned on at some time and then stayed on. And we use the function u, which is, again, it's this function u of t minus 5 is going to be 0 for t less than 5, and it's going to be 1 for t bigger than 5. So after 5 seconds, say, this object was basically in harmonic motion, basically the solution of the homogeneous equation with the initial conditions given here, and then at 5 seconds later, a force upward of 1 unit is applied and it stays on for future time. And we saw how to determine the solution using Laplace transforms. And again, using our formula, we realized the Laplace transform of this function u of t minus 5 was just this exponential divided by a factor of s. Well, now when we go to change this to an impulse force, which is at an instant of time, so it kind of turns on and off at the same moment in time, it's like an impact. The only thing that changes is, in our formula, was the Laplace transform of our force. So instead of having this e to the minus 5s over s, we now have just e to the minus 5s, and we don't have the other factor of s there. So that's the only difference in these two problems. So we have our problem. We plug it into our formula that we derived for second order initial value problems. Remember, capital F of s is just the Laplace transform of whatever we see on the right side. We know what that is. In this case, it's e to the 5s. Our mass is 1 because of this term. Our a is 2 because of this term, and our k is 1 because of this term. Our x of 0 is 1, and our x prime of 0 is 0, so we can plug all these things in. And we know that our solution to the initial value problem, all that we have to do is compute this inverse Laplace transform. And again, because of linearity, we want to split this numerator into terms that will make it easier to compute, or easier to look up these inverse Laplace transforms in a table of formulas. So in this case, writing it this way is useful because our denominator actually factors as a perfect square, s plus 1 squared. So because of that, splitting this s plus 2 as an s plus 1 and then plus another 1 over here is useful because it simplifies the second term, allows us to cancel a factor of s plus 1. So what we have is, in the third term, for example, we have 1 over this s plus 1 squared. Again, thinking of our basic formulas, 1 over s squared, that's the Laplace transform of t. But since we've shifted it, this s plus 1 is the same thing as s minus a minus 1. That's the same thing as taking t and multiplying it by e to the minus 1 times t. So that's where this third term comes from. The second term, again, this s plus 1 factor cancels, so we really have 1 over s plus 1. The Laplace transform of 1 over s is just 1. I'm sorry, the Laplace transform of the function 1 is 1 over s. So again, we're just taking the function 1, multiplying it by the exponential here, e to the minus t, because of the shift. Now, the first term is just a product of two Laplace transforms. The first is this e to the minus 5s, which we know is the Laplace transform of our Dirac distribution. And the second is the one we have from our third term over here, which we already identified as t e to the minus t. So because we have a product inside of here, the inverse Laplace transform is given by this convolution. But remember what we said, when you integrate a Dirac distribution times another function, you're really just looking at the input inside here, and you're looking at the variable that you're integrating in this case z. So if I solve this for 0, it's saying that z has to be t minus 5. But we also have to consider the fact that there's a t in our limit of integration. And this is explained in the notes that I have in the this week's folder. Is the consequence of having this t is describing a piecewise defined function. So in effect, this formula that we're going to get for this convolution only applies for time after the moment of impact. It doesn't apply before. So we're going to have to define our function as a piecewise defined function. And again, all we did here in this convolution then is we restrict to the t plus t bigger than 5. That's because of the t up here. And then otherwise, we just take our expression highlighted here, solve this for z, set this equal to 0 and solve for z. So z is t minus 5. Now I just plug in t minus 5 into this function, and then that's what gives us this first term. So there's two parts here. The use of the direct distribution is allowing us to just simply write this function as the first term, but because of the t up here, which is explained in the notes, we have to restrict our attention to t bigger than 5, which again should make sense because this impact force doesn't occur until 5 seconds later or 5 minutes later, whatever time units you're using. So when you're having a problem like this, you're always going to get a solution of this general format. You're going to have basically your homogeneous solution is for t smaller than 5, because before 5 seconds, the right-hand side is 0. There's no external force. But at this moment, t equals 5 is when there's an impact force. So that gives us this added term only when t is bigger than 5. And if we look at the graph, we see what happens. In red, and both of these graphs, if we graphed the homogeneous solution and this piecewise defined function, they both match for the first 5 seconds. And if there was no impact, you'd see this red curve would continue in the solution that we would get by solving the homogeneous problem. But because of the upward impact force, in this case of a unit in magnitude, this caused the object to be, as it was falling or vibrating on the spring and coming down, at 5 seconds, the impact caused it to be thrown upward. But once it was thrown upward, that impact no longer has any effect, so it's just momentum transferred from whatever it came into contact with. So that momentum transfer caused it to move in this other direction, and then the spring force took over after that, and the air resistance took place after that. So once t equals 5 and that impact occurs, all that was really doing was transferring momentum, throwing the object upward, and then the object is just following the homogeneous solution with different initial conditions now. In a sense, we think of t equals 5 as a new initial observation right after the impact, and that would give us a solution according to those new initial conditions, which would be defined by the impact.